Look up at the night sky. To your naked eye, it is a silent, static tapestry of light. For a very long time, we thought the universe was exactly that quiet. But when we build instruments sensitive enough to actually listen to the cosmos, we realize the void is anything but silent. It is roaring. I want you to imagine the deepest, darkest patch of space, a region so utterly empty that light itself seems to have abandoned it. Now imagine a pulse of energy erupting from that absolute darkness so impossibly intense and so perfectly timed that it shatters every rule of physics we have spent the last H100 red years writing. We have recently intercepted a signal from deep space, and I am not talking about the random, messy static of collapsing stars or the chaotic whisper of the cosmic dawn. I am talking about a highly structured, overwhelmingly powerful burst of radio waves crossing billions of light years of empty space to reach our detectors, a signal that, according to the standard model of cosmology, simply should not exist. When I first looked at the data, I felt a profound sense of awe because anomalies like this force us to confront a thrilling reality. Either our most fundamental equations governing the fabric of space and time are missing a massive piece of the puzzle, or there is a mechanism out there generating energy on a scale we cannot even begin to comprehend. Today I'm going to take you to the very edge of what we know. We will unravel exactly what this anomaly is and why it threatens to break our understanding of reality. If you want to unravel these cosmic mysteries with me, make sure you subscribe to the channel. Let us journey into the dark together. If you are old enough to remember tuning a classic analog radio, you know the sound of the empty space between stations, that crackling, hissing static. When I was younger, I used to slowly turn the dial, listening to the white noise, trying to find a clear voice hiding in the chaos. What most people do not realize is that a fraction of that static you hear on an old radio or the snow you see on an untuned television set is actually the ancient whisper of the universe itself. It is the leftover heat of the Big Bang washing over the Earth day and night. For nearly a century, astronomers have been tuning the ultimate cosmic radios. We call them radio telescopes. Huge sweeping dishes of metal, some the size of entire valleys pointing up at the heavens. We are not looking for light we can see with our eyes. 3. We are feeling for invisible waves of electromagnetic energy stretching across the cosmos. To understand why the signal we recently detected is so impossible, we first have to understand the fundamental rules of how energy travels through the vastness of space. Think about standing in a completely dark field with a small flashlight. If you shine it at a tree 10 feet away, the light hits the trunk clearly. The beam is tight and the energy is focused. But if you try to illuminate a mountain miles in the distance with that same flashlight, you will see absolutely nothing. It is not that the light stops existing. It is that as the light travels, it spreads out. By the time it reaches the mountain, the energy has dispersed over such a wide area that it is completely undetectable. In physics, we call this the inverse square law. The further away you get from a source of light or radio waves, the weaker the signal gets, and it weakens very, very quickly. A distance 2 times further away means the signal is 4 times weaker. 3 times further means it is 9 times weaker. Now stretch that distance not across a quiet field, but across billions of light years of absolutely empty space. When a massive star reaches the end of its life and collapses in on itself, creating a supernova, it shines with the brightness of 10 billion suns. That is the kind of raw, very chaotic power we are used to observing. But because it is so incredibly far away, by the time those radio waves cross the intergalactic void and wash over our planet, they are fainter than the kinetic energy of a single snowflake hitting the ground. Our telescopes have to be marvel of engineering just to detect them. We expect the cosmos to be faint. We expect it to be messy, chaotic, and spread out. The things that usually make noise in the radio spectrum are massive, long-lasting events. Supermassive black holes devouring stars, rotating neutron stars pulsing like lighthouses, or vast clouds of hydrogen gas cooling over millions of years. These processes take time, and their signals are steady, wide, and predictable. They are the natural symphony of the universe. But that is not what this new signal was. What hit our detectors was a burst of radio energy so profoundly intense and yet so incredibly brief that it lasted for only a few milliseconds, a fraction of the blink of an eye. For that tiny sliver of a second, this single burst outshone entire galaxies. I want you to really think about what that means based on the rules I just laid out. To overcome the extreme dissipation over a distance of billions of light years, and to pack all of that unimaginable energy into a pulse lasting just 1,000th of a second requires a mechanism that we cannot find in our physics textbooks. It is like standing on a beach in California and hearing someone whisper a secret from the coast of Japan, clear as day over the crashing of the ocean waves. It defies the laws of energy dispersion. Something out there is generating power on a scale that makes the nuclear furnace of our own sun look like a dying spark. And it is doing it with a precision that leaves us completely baffled. The foundation of what we thought we knew about cosmic energy has just been violently shaken. When a detective arrives at a crime scene, the first thing they look for is the physical evidence that tells a story about the timeline. A warm cup of coffee on the table tells you someone was here 5 minutes ago. A layer of dust tells you the room has been abandoned for years. In astrophysics, we have our own cosmic forensic tool. It is called dispersion, and it allows us to measure precisely how far a radio signal has traveled across the universe. Space looks completely empty, but it is not a pure vacuum, spread out across the immense voids between galaxies. There is a very thin, invisible fog of ionized gas composed mostly of free electrons and protons. When a pulse of light or radio waves travels across billions of light years, it has to plow through this tenuous fog. Now, think about what happens when white light passes through a glass prism. The prism bends the light, separating it into a rainbow because different colors or different wavelengths of light travel through the glass at slightly different speeds. The exact same thing happens to a radio pulse traveling through the intergalactic fog. The higher frequency radio waves slice right through the electrons with very little resistance, arriving at our telescopes first. The lower frequency radio waves get slightly dragged down, slowed by the electrons, arriving at our dishes a fraction of a second later. By measuring the precise time delay between the high pitch of the signal and the low pitch, we can calculate the exact number of electrons the signal encountered on its journey. When my colleagues and I analyzed the dispersion of this anomalous signal, the numbers were staggering. The delay between the high and low frequencies was so wide that it proved the signal had crossed more than 8 billion light years of intergalactic space. Think about that timeline for a moment. This pulse of energy began its journey long before our Earth and Sun even formed from a cloud of cosmic dust. It has been traveling through the silent dark for more than half the entire age of the universe. That alone would make it an extraordinary discovery. But when we zoomed into the microsecond structure of the pulse, the mystery deepened into something truly unsettling. Normally, when a catastrophic event happens in space, like a star exploding, the energy is thermal. It is chaotic, hot, and noisy. It is like a bomb detonating. The energy sprays out in all directions at all frequencies with random polarization. It is messy because nature left to itself tends toward disorder. This signal was not messy. It was intensely coherent. To understand coherence, imagine a crowded stadium where 10,000 people are shouting at the top of their lungs at random. It sounds like a roar of white noise. You cannot pick out a single word. That is a thermal signal. But now imagine those 10,000 people suddenly falling silent, taking a breath, and shouting the exact same word at the exact same millisecond in perfect unison. The sound wave becomes sharp, very organized, and carries an enormous concentrated punch. That is what we saw in the data. The radio waves were not radiating randomly. The electric and magnetic fields were oscillating in absolute lockstep, polarized with surgical precision. For that level of coherence to occur, trillions of billions of charged particles must be forced to move together as a single unified entity. And there is something even more troubling. In physics, there is a strict rule governed by the speed of light. Nothing can move faster than light, which means an object cannot change its brightness faster than the time it takes light to travel across that object. If an entire galaxy were to flash, it would take hundreds of thousands of years for the flash to appear uniform, because the galaxy is vast. Because this pulse lasted only a fraction of a millisecond. The physical engine that created it cannot be larger than a small city. Imagine an engine no bigger than Manhattan outputting more energy in the blink of an eye than our sun produces in an entire year with the precision and coherence of an engineered pulse from 8 billion light years away. Nature does not easily build machines like that. Every known astrophysical explanation was about to hit a brick wall. When I face a cosmic mystery, my first instinct is to look at the most extreme laboratories nature has to offer. For decades, whenever we encountered impossible bursts of energy, we pointed our telescopes toward the remnants of dead stars. Let us consider the prime suspect in our cosmic investigation, an object known as a magnetar. To understand a magnetar, you have to understand the brutal force of gravity. When a massive star dies, it runs out of nuclear fuel, and its core collapses inward. Imagine taking the entire mass of a colossal mountain range and crushing it down until it is the size of a single grain of sand. The density is simply incomprehensible. Now picture an object with that kind of density, roughly the size of a small city spinning on its axis, hundreds of times every single second. This is a neutron star. A magnetar is a rare type of neutron star with a magnetic field so intense that if you place one halfway to our moon, the invisible magnetic force would literally rip the iron right out of your blood. For a long time, we physicists believed that magnetars were the engines behind these mysterious radio bursts. The theory made sense. The crust of a magnetar is under immense stress. Occasionally, the crust cracks, causing a starquake. This violent shift twists and snaps the magnetic field lines, much like winding a thick rubber band until it violently breaks. The snapping magnetic fields launch a shock wave of energy, theoretically producing a fast radio burst. But when we applied this model to the signal we just intercepted, the mathematics collapsed. Here is where we hit a massive glaring paradox to generate a radio pulse bright enough to cross 8 billion light years and still hit our dishes with such fierce intensity. The sheer volume of energy released at the source must be catastrophic. Remember the absolute coherence I talked about earlier. The perfectly synchronized march of radio waves. That precise structure requires a highly stable magnetic field to act as a megaphone focusing and channeling the beam outward into the void. But the raw explosive power required to send a signal across more than half the known universe is so violent that the radiation itself would instantly vaporize the very electrons trying to ride the magnetic lines. It is like trying to force the entire water pressure of the Hoover Dam through a standard garden hose. The hose does not just stretch or leak, it completely obliterates. The immense energy of the blast would rip the magnetic megaphone to shreds, scattering the radio waves into a messy, chaotic thermal soup. Yet, the signal we received was clean, it was pristine, it arrived perfectly intact. And the paradox only deepens when we look at the environment surrounding this hypothetical engine. In order to fuel a burst of this magnitude, the space immediately surrounding the source must be incredibly dense, packed with swirling plasma and stellar debris. But if the environment is thick with matter, the radio waves should be absorbed, very scattered and muffled before they ever leave their home galaxy. It is like trying to shine a high-powered laser through a solid brick wall to get a sharp, coherent pulse to escape into intergalactic space. The area immediately around the engine must be completely empty, like a vacuum-sealed clean room. Do you see the contradiction? We are trapped in a profound logical nightmare. The engine must be overwhelmingly violent to generate the power to reach us. But if it is that violent, it destroys the mechanism needed to focus the beam. The surrounding environment must be incredibly dense to fuel the star, but it must also be perfectly empty to let the pulse escape unaltered. We have stretched our physics to the absolute limit. We have bent the equations of general relativity and quantum mechanics, trying to force this impossible data into our existing models of dead stars. But the math refuses to cooperate. Nature is showing us a phenomenon that contradicts itself at every turn. When the natural explanations begin to fail, we are forced to look at the edge of the theoretical abyss. We have to ask a deeply uncomfortable question. If dead stars cannot do this, what can? When standard stellar mechanics and magnetars fail to provide a clean answer, we are forced to widen our lens and consider physics that operates at the very boundaries of our current understanding. If the engine is not a conventional dead star, what kind of exotic physics could possibly account for a signal this powerful, this structured, and this precise? Let us venture into the realm of theoretical constructs. For decades, some theoretical physicists have studied topological defects in the fabric of space and time itself. These are known as cosmic strings. Imagine the universe during its earliest moments, a fraction of a second after the Big Bang, undergoing a massive phase transition, much like water freezing into ice. When water freezes, imperfections form along the boundaries where crystals meet, creating cracks and lines of stress. If space itself froze in a similar way during the birth of the cosmos, it could have left behind microscopic, unimaginably dense folds of energy stretching across light years. These cosmic strings would possess gravitational fields unlike anything else. And under specific conditions, they could oscillate, snap, or interact with ambient magnetic fields in ways that release localized, hyperconcentrated beams of electromagnetic radiation. A pulse generated by a cosmic string would naturally bypass many of the limitations that plague magnetars. It would not rely on a dense plasma environment to fuel itself, and its inherent topological geometry could naturally focus energy into a coherent laser-like beam without tearing the source apart. It is a radical hypothesis, certainly, but when conventional physics hits a brick wall, we have to consider phenomena that exist beyond our standard laboratory reach. Another possibility takes us into the domain of quantum electrodynamics, on a scale we can only test through mathematics. We know that the vacuum of space is never truly empty. It is a roaring, boiling sea of quantum fluctuations where virtual particles constantly pop into existence and annihilate each other under extreme conditions. When magnetic fields reach values that defy imagination, the very structure of the vacuum can become polarized. It acts like a nonlinear lens, bending, magnifying, and transforming low-frequency waves into high-intensity coherent bursts of radio frequency. Think about what that means for a moment. The signal we detected might not be the result of an object moving through space, but rather a sudden violent phase transition of the vacuum itself. A momentary tearing and snapping of the quantum foam, releasing energy that was locked away in the very fabric of empty space. When you trace the math of these exotic models, a sobering realization washes over you. The universe is not obligated to make sense to our everyday intuitions. We spent centuries building a physics based on what we can touch, see, and measure in our terrestrial laboratories. But the cosmos operates on scales of energy and time that dwarf our imagination, utilizing mechanisms that turn our neat little categories upside down. We are standing at the edge of a vast, uncharted ocean. The signal we caught from 8 billion years away is a message not written in words, but written in the harsh, uncompromising language of extreme physics. It tells us that there are engines at work in the dark, shaping reality in ways we are only just beginning to fathom. History teaches us that whenever humanity builds an instrument capable of seeing deeper into the dark, nature responds with something we did not expect. Think back to Galileo pointing his primitive telescope at Jupiter and discovering moons that had no business orbiting another planet according to the geocentric dogma of his era. Or think of Edwin Hubble looking at faint spiral nebula and realizing our entire home galaxy is just one tiny speck in an ocean of millions. Every single time we think we have the universe neatly mapped out in our equations, reality pulls the rug out from under us. This signal from 8 billion light years away is not just a strange quirk of data or a glitch in a radio telescope. It is a signpost pointing toward a massive blind spot in our comprehension of physics. Whether these fast radio bursts are born from the chaotic death throes of binary star systems interacting with exotic magnetars, or whether they represent topological scars from the dawn of space itself, they force us to humble ourselves before the scale of the cosmos. We live on a fragile rock orbiting an ordinary star in a quiet arm of a standard galaxy. Yet sitting right here in our offices, using the power of human mathematics and engineering, we can detect a flash of energy that occurred before multicellular life even evolved on Earth. We can measure its polarization, retrace its intergalactic journey through the cosmic web, and map it back to its distant host galaxy. That is the true triumph of science. We are finite biological creatures bound to a speck of dust. Yet, our minds are vast enough to decode the history of the universe. When you stand back and look at the totality of what we have uncovered, the implications are staggering. We are not just passive observers sitting comfortably in a cosmic backwater. We are an active part of the universe waking up and studying itself. Think about the journey of that single radio pulse. It left its source 8 billion years ago, long before the solar system existed. It crossed the dark, silent expanses of intergalactic space, brushing against clouds of gas, bending through magnetic fields, and finally crashing into a metal dish on Earth exactly at the precise millisecond our instruments were tuned to catch it. That is not just an observation. That is a connection across deep time. When we confront mysteries of this magnitude, mysteries that push the absolute boundaries of general relativity, quantum mechanics, and cosmology, we realize that the journey of discovery is never finished. Every answer we claw our way toward only reveals 3 deeper, more bewildering questions. And that is precisely where the beauty of science lies. We do not need a universe that is simple, safe, and comfortable. We want a universe that is vast, challenging, and endlessly deep because it forces us to grow, to invent, and to expand our minds beyond their original limits. Building the next generation of telescopes, analyzing petabytes of cosmic data, and pushing the frontiers of theoretical physics is an immense endeavor. It takes thousands of dedicated scientists, engineers, and curious minds working together across generations to shine a light into the dark. If you want to support our ongoing mission to decode the deepest secrets of the cosmos and help us keep exploring these mind-bending frontiers, you can use the Super Thanks button below this video to contribute directly to our research and production. Your support allows us to dive even deeper into the mathematics and the mysteries that shape reality. Because when we look up at the night sky, we are not just looking at stars and galaxies, we are looking at our own origin story. Every heavy element in our blood, every carbon atom in our cells, and every spark of consciousness that allows us to ask these questions was forged in the violent heart of ancient stellar furnaces. We are the cosmos thinking, wondering, and searching for its own reflection in the